13A, what do you got? 8 pi. 13B? No. Colin, what'd you say? 128 pi over 5. C? 256 pi over 15. Okay. C is 256 pi over 15. D?
192 pi over 5.
192 pi over 5. 15A?
32 pi over 3.
32 pi over 3. 15B? 64 pi over 3. Okay, 22. 368 pi over 3. 25.
It's got like 4.3 pi. Yeah, I got 2 natural log 2 pi.
2 pi times natural log of 2.
Yeah.
2 pi natural log of 2, which might be that decimal. Now, this answer book has pi ln4, but again, in this answer book, if you look at their work, they set up the integral, and then they do it with antiderivatives, right? Older book, so they do, because all these could be done with antiderivatives. So you see the alpha so forth. So it comes out pi ln4. Your calculator, of course, takes ln4 and turns it into 2 ln2, so which of course is okay. All right, and then 38, 39 we'll look at. 49A. We got 49A.
32 pi over 3.
No, there's no pi because there's square cross section, so there should be a pi. Joe, what'd you say?
Oh, actually,
128 over 3. B. 32 root 3 over 3. And C. 16 pi. Okay? All right. So, 25. Was that the first one, or did we have one? I thought there was an earlier one that we didn't sound too confident. What was that? 15, 13B. Okay, so what are the curves on 13B? What are we supposed to? It's y equals
square root of x, y equals 0, x equals 0.
So it's this
y
region.
equals 0, x equals 4.
X equals 4.
Yeah.
And then it's revolved about what?
On B?
In B. The y-axis. Okay, revolved about the y-axis. So y equals square root of x would be here. X equals 4 would be here. So we're looking at this region, and we're going to revolve it here. So we're picking up this region, and we're going to revolve it this way. Now, I'll probably do this one time here and not the other, but what will happen is that region would get revolved around over to here, and so our slices would be what shape? Washers, right? There's empty space, okay? So again, remember what we said yesterday. Anytime you're doing a revolving problem, it's always going to be one of these two options. And to be honest, most of the time it's washing. Okay, most of the time there's empty space. Now the only time here, I think one of the problems they revolved around, wow, that's a great line. X equals 4, when they revolved around x equals 4, right? So if you take this and revolve it there, there's no empty space there, right? It's a solid, it revolves there, so there's no empty space. So that would be just solid circle slices, like the lemon exercise. But you go back through the AP test, you go back through, the volume of solid problems the revolution problems that you run into on the AP test, almost always that region has some empty space there between it and the axis of revolution. So washers are pretty common. Okay, but when it's revolution, it's got to be one of those two. It's got to be one of those two. Okay, and like I say, pretty common that it's washer. So the washer, so the slice, and again, the other thing you always want to know then is you got to draw from the axis of revolution. So this strip is your big R, and this strip right here would be your little r, right? Because that's what you need. You need big R and you need little r. Okay, so big R, so the length of this strip is what? It's this x value, 4, minus this x value, No,
Zero.
0, right? So wouldn't big R be 4 minus 0? And little r would be this x value, and that's where we have to solve this. Remember, anytime we have okay, and that's common because you got to keep that in mind, and that's why you keep hearing me say this x value minus this x value, because I'm reminding myself that what I should be looking for here is an x equals, right? I need this x value. Oh, it's x equals 4. I need this x value. Oh, it's x equals 0. I need this x value. Oh, it's the parabola. Oh, what's its x value? Oh, I got to get x equals, right? So that's just a constant reminder of myself. That's what I need. If all you think about is, oh, I just got to take this line minus this, or then I say, oh, I got to take the parabola minus this, you'll just go look at the parabola and you'll say, oh, square root of x. You know what I mean? You won't think of that. Or maybe you just remember that anytime you have horizontal strips, it's got to be what? It's got to be x equals, right? Anytime it's horizontal strips, it's got to be x equals. Anytime it's vertical strips, it's got to be y equals, which is our normal way to do it. So that's a way to remember it too. Okay, just memorize horizontal strips always have to be x equals. So x equals y squared. So anyway, it's this x coordinate y squared minus this x coordinate. So it's y squared minus 0. So that might be where we had our problem. So pi big R squared, and it's important to put this out in front. Because if you don't, if you just put it here, then a lot of times what people do is they do this, and then the pi is only times the big R squared, unless you put parentheses around everything. But in these problems, you end up with enough parentheses the way it is, where you might not want to do that. So putting the pi out in front is probably best. Okay, big R, this is a pretty easy one though. Big R squared, you have a lot of parentheses. So big R squared minus little r squared, and it goes from? It's 2, right? Because this is the point 4, 2 right here, and these strips fill the space from 0 up to a y value of 2. 0 to 2. Okay? All right, so that should be that one. All right, what else? 25? 25 is our next one. Okay, what was the region, Joe?
It was y equals 1 over the square root of x plus 1. Y equals 0.
Okay.
X equals 0. And x equals 3.
X equals what?
3.
3.
And it's rotated.
So this kind of comes down like this. X equals 3 is over here. Like so. So it's something like that.
And it's revolved around x.
Revolved around the x-axis.
Yeah, sorry. That's why.
That's where you screwed up.
Yeah, I was still thinking it was revolved around x equals 6.
Oh. Okay, so this would be one with no empty space then, right? This would be one with no empty space. This would be the other side of your region would be here. This would be your slice, right? This strip is the radius of that slice, okay? So we just need that radius, that strip. Well, it's the y value, which is this, minus that. Yeah, so that's pretty straightforward one, isn't it? So, okay, makes sense. So you got this squared pi dx. So pi r squared 2. Okay? All right, 38. 38 said to verify, it said use the disk method. Well, what's that mean? Yeah, make it so the slices are a circle, right? That's all that's saying. Okay, make the slices, and so it does go. Now, we actually did one of those yesterday. It's similar, right? We had a shape that we said when we revolved it, it would make it come. So what shape was that would make it come? Triangle. So you just need to draw yourself a triangle. So, Bo, did you do this?
Yeah.
What'd you do?
Also, I drew a triangle.
How?
Digging it origin up.
So you just went up like this.
Yeah.
Okay? And then drew a vertical line over here somewhere?
Yeah.
Okay. Right there. Now that's not the one we had yesterday. Yesterday we had a line coming down like this that made a triangle. It doesn't matter. Right? And where are you going to revolve this?
X-axis.
Okay? So you had some options here. We did it differently in the first block. We did it like the one we did here. Now, to be honest, that made a little more difficult equation than this one's going to be. This is probably the best way to do it. Okay? Now, what?
I think they used line up and down.
So, Let me just do this. So when we revolve this, we're gonna get a cone. Okay, and so you did a strip here,
Yeah,
right?
so,
So one slice is gonna be there, right there. It's a circular slice, okay?
so you can determine your big R and little R.
I don't need a big R and little r, I don't think.
Just your R.
I just need this R, right? So it'd be this strip right here.
Yeah.
So what is that? That's this Y value. What is that?
Height is
Yeah.
not.
Okay, and we need the equation of that Y, right? That's what we need. So you created it, right? So you just want to call it Y equals X? That'd be the simplest probably. So the line Y equals X, right? So what is this Y value? So we can call that R. Radius of this, so that's this Y value be X minus 0. Right? And so that integral, so it would be pi times R squared. And the strips go from what to what?
0 to X. Or, yeah.
0 to H. Because this right here is the height of that cone, right? So this distance here has to be H, okay? So the strips, if it's the lines Y equals X, we create a cone. We just do this, 0 to H. The problem we have here is, I guess, this isn't going to work. We're missing a piece here, and that's my fault. I let you get away with it. When Trey said Y equals X, I shouldn't have let him use Y equals X.
Doesn't it say just use R as the radius?
Yes, we need a cone that's got a height H and has a radius R. What would be the radius on this cone here? No.
Or,
What would this distance be right here? If this line is Y equals X, what would this distance be right here? Would it just be H? I mean, if it's Y equals X, then whatever your X is, that's also your Y. So if this is H, this is H. So this would be a cone that has H as its height and H as its radius. We can't have it. Okay? So what, I need to change the equation of this line. Yours was what? Use it. But here's what I'm saying. We can't assume that this is a slope of one line. What do we need this distance to be right here?
R.
We need to call that R. Now it has to be a different R than what we were using here though, right? So if I'm going to call this point H comma R, little r, right? Then that would be R right here. Now what's the equation of this line now?
Y equals R.
No? What's the slope of this line? It's R over H, right? It's rise over run, right? Rise over run. So it's R over H X. That's what I need. Okay? That's the equation of my line. Y equals R over HX. So now, I'm gonna use big R now because I use little r for this. So now I want this strip, which is the radius of my slice, right? I'm gonna call that big R. So now big R is gonna be this Y value, which is what? R over H X minus 0. Now I come over to here, and now my integral is pi times R squared, so now it's going to be R over H X squared. Now type that into your calculator. Okay. That was only going to give us a cone where the height and radius were the same. Okay, that was going to give us the area, which of course would be, a cone is 1/3 pi R squared H. Well, that'd be 1/3, if R and H were the same, that'd be 1/3 H cubed. If we would have typed in this other integral we had, we would have got 1/3 H cubed, which would be right for a cone where the radius equals the height, but that's not what we want to do. Okay, type that into your calculator. Now we could do it with just antiderivative and algebra, and R and H are just constant. Do you get 1/3 pi R squared H? I hope. Can you type that in? And the calculator will do it for you. When you tell it to do that integral with a dx, means with respect to x, it'll treat all the other letters as constants, which is what we want. Okay, that's what we get. Okay, so there you go. So we verified that a cone would be that. So we want to do a similar thing for 39. 39 says we want to verify that a sphere has the volume 4/3 pi r cubed. So how could we create a sphere? What could we revolve to create a sphere? Semicircle, right? I think we had one, we talked about that too. Take a semicircle of radius what? Well, you get the circle, but it would be unnecessary because the circle would revolve onto itself, you know. Right? So you only need it, just like the length, right? We only need half. So we need it to be radius r. So this would be r and negative r, right? And we're going to have a strip right here. So we need this y value minus this y value, so we need an equation for this circle. What's the equation of the circle? Right? X squared plus y squared equals r squared, but then solving for y, the top half, so we'd have that. So that's that equation right there. So what's my, so here's my, so my slice would be here, right? This is my radius. Again, I'm going to use big R because I'm already using R for something else. So the radius of my slice would be the top y value, which is that, minus 0. And so my integral to add up is the area of this slice, which is about pi times this radius, which is that right there, squared. Square that. And it would go from negative R to R. Okay, that's it. Type that in your calculator, and lo and behold, you will get 4/3 pi r cubed. Okay? So, kind of nice to show the calculus, you know, that we can create these geometric shapes by revolving two-dimensional regions, take their equations, we can put them into these integrals, and we can verify these geometric formulas that we've known forever. But it's like, where do they come from? Why do we know that? This is one way to show that's what they would do. Okay? All right, so you want to look at 49. Now, I'll be honest, the pictures on 49 I almost think are less helpful, to be honest with you, more confusing. And you're not going to have those pictures when you do them. So to be honest, I would just kind of ignore those pictures. Now, we can think about what we did, you know, yesterday to help us a little bit, but what do they tell you? Just give me the directions. What do they give you as far as the region? Bounded by what? Yeah, what region is the base? So the base is x squared plus y squared equals 4, which is just a circle of radius 2. What else do they tell you? Well, they tell you about the slices. Perpendicular to the x-axis. So we know our slices are going to be here. And what are they in part A? Part A, the squares in part A. So what that means, that's exactly this picture right here. Okay, that's exactly this situation here that we had yesterday, and we just have squares. Whoops. We have squares coming up off the page. Okay, and so it creates this kind of strange shaped solid here. So you just have to picture now. If I, you know, and you can try to draw it. You can kind of hear it. Oh God. Try to draw your circle. Here would be a strip, and coming up off there's a square. Here would be a much smaller. Oh man, I've done better. Let me see. Okay. I need to look at it.
Yeah, that's the problem.
That was the problem. Right. Or here, like right through here, you have a smaller strip, so it's going to be a smaller square. Right? Because I don't. Anyway, trying to see these three dimensions. Okay, but not necessary. Or think of it this way. So coming up off the page right here is a square. right? Right here, there'd be a small square coming up off. But the idea is, if we understand this right here, all we need is the area of what a slice is, and the slice is a square. So the area of a square is just S squared, where the strip is one side of the square. So all we really need is, what is this strip? Well, the length of this strip. Well, it's this y value. What's this y value up here? Isn't it that? And down here it's negative square root 4 minus x squared, right? We just solved for y. So it's this y value minus this y value. That'd be root 4 minus x squared minus negative root 4x. So what is s? What is this side of a square? 2 square root 4 minus x squared, right? It's this minus that. So all we need here is an integral, where in here we have the area of a slice. And a slice is a square, and this is the side of the square. So it's simply that square. That's it. From the slices fill the space from -2 to 2. That's all you need. And it gets even easier than that, because now we go on to what? Equilateral triangles. What is this? Now you just envision, okay, coming up off of here are triangles, where this is one side or the base of the equilateral triangle. Well, what do we say the area of an equilateral triangle is? Right? The base, root 3 over 4 times the base squared. The base is this strip right here. So what is it?
Square root of 3 over 4 times that square.
Square root of 3 over 4 times, or no, I'm sorry. The base is 2 square root 4 minus x squared. It's the same thing that s is, right? It's that strip. And so our integral is -2 to 2, root 3 over 4, and then it's 2 square root of 4 minus x squared dx. In other words, it's the same exact one, just has a root 3 over 4 out in front. Will it be the same way every time? Well, pretty much, if there are these basic kind of problems. And that last one was semicircle. So now we just imagine semicircles coming off of here. Now, if you have a circle base with semicircles coming up off of it, what do you really have? Isn't it, well, half. Don't you have half a sphere? A semisphere, hemisphere? Okay, snow globe, yeah. Right? And so we just said a sphere is 4/3 pi r cubed, so this should be 2/3 pi r cubed. The radius is 2, so that's 8, it's 16 pi thirds. This answer should be 16 pi thirds, I think it was. Right? But that's beside the point, just to double check. So coming up off here are semicircles. So let's try this one more time. Ooh, let's be honest. Strip, semicircle. Semicircle. Let's do another one. Bigger semicircle. Oh, got worse. Okay, anyway. All right. So, what is this strip? What part of the semicircle is this strip? It's the diameter of that semicircle. So, coming up off of here is a semicircle, whatever. That strip is the diameter. So, we would say D is equal to 2 square root of 4 minus x squared. And what is our area of a semicircle? 1/8 pi, and then d squared. From -2 to 2. So the only thing that really changed is those numbers out front, because every one of those was the strip squared. Because if you look at these formulas, that's basically what they are. The strip is the side of the square, the strip is the base of the triangle, the strip is the diameter of the semicircle, and every one of those you square them, and then they just have another number out front. So it's not too difficult once you get the hang of that. Now, we can make it a little more challenging. We'll look at a couple of problems here in a minute.
Oh, that's
So yeah, you got. I mean, this is too easy. You guys are way
too challenging.
Way above this. All right. So take out your 2016 packet, please. 2016.
252, that's got a name, I think it's Taurus or something. Cylinder.
I've worked a problem like that a long time. All right, 2016. Yeah, that little packet, 2016, we've done a lot of it. Well, I don't know how much we've done. I think we've done quite a bit. Oh, I'm sorry, no, wrong one. 2014.
You got to be kidding.
But keep that 2016 handy because we're gonna do it, not today, but we'll do it, maybe Monday.
You're talking about free response.
Talking about free response 2014.
Too many packets for this class.
All right, number 2, let's do A first, and then do B. Now, B's the one that you're going to have to think about a little more because it talks about a cross section, but it talks about it being isosceles right triangle. So you're going to have to think about it and talk with each other maybe about it a little bit. But A, you can. Hopefully, A will be pretty easy. So go ahead and do those. And go ahead, it says don't evaluate, but go ahead. Well, no, I take it back. It does say to find because this is a calculator one. So they did want you to go ahead and find the answer. So go ahead and do that. What's an isosceles right triangle? It is not an equilateral triangle. What's an isosceles right triangle? 2 equal sides, but it's a right triangle. So which 2 are equal? It can't be the hypotenuse, right? It's got to be the 2 left, right? So that's an isosceles right triangle. So it's 45-45, right? It's got to be that kind of situation.
It's 0 to 2.3. So 7 equals x squared, x to the 4th minus 2.3x cubed equals 0. You take off x cubed equals 0.
Be any three of the legs in
No. Isosceles right triangle only has 2 legs.
there? I mean, and then, but couldn't it be either one of them?
It can be either one of the legs, but not the hypotenuse. It can't be the hypotenuse.
Just as it says with a leg in line.
Hypotenuse is not a leg, right? If it would have said one of the sides, that would have been a problem. Okay. When it says one of the legs, it means.
Wait, so we don't use the area equation that you have in our notes.
Right, because that's an equilateral triangle. That's different. That's a 60-60-60. That's a different thing. So that's why I said, somebody in the other class said, well, I thought we couldn't do an isosceles right triangle. That's not what I said. I said these 5 are the 5 I gave you in that list are the ones that are going to be on our quiz. But there are other slices. But again, you just got to understand the concept. You need, in your integral, you need the area of the slice. So it's an isosceles right triangle. One of the legs is in the region. So that means your strip is one of the legs, right? What's the area of that triangle right there? Right? Just label this. Jesus. Right? Label that B for base. You can write the area of that triangle. Right? Maybe one of my great drawings would be helpful at this point. Wouldn't this be a strip right here? Coming up off of that?
What's the answer?
There'd be a strip right here, coming up off of that. Isn't that what you'd have coming up? Yeah, isosceles right triangle means the 2 legs are equal. Isosceles means 2 equal sides.
I had it where the hypotenuse was the.
It says leg.
Okay, but it says.
Right, yeah, I got you.
Yeah, with a leg in R. Because you're right, I'm going to talk about that in a minute. 49D, I don't know if you looked at it, but 49D had it where the hypotenuse was in the region, and then the 2 legs, that's not a very good drawing, but the 2 legs came up, and the hypotenuse was in the region. We'll talk about doing that one too, because we should be able to do that also.
What's the answer?
To
A and B.
Anybody, what are you getting for A? 98.8 something.
1.609.
What about B?
Don't say it.
Well,
I got
I
1.609.
it's not like you hear 98.8 and go, oh yes, now I get how to do it.
Yeah.
You know what I mean?
Yeah, somebody give me the equation for
Yeah, somebody just
walk me through it.
Somebody got the answer for walk you through A?
Yeah. Joe.
I got the wrong answer.
Can
I
you
got
guys answer
20.
please?
Well, we will. We'll walk through it. We'll walk through it. Nobody has an answer for B yet?
I have an answer, but
Faith, you got an answer.
Is 3.57.
You do too.
Not for B.
You don't?
Mine's 1.609. Is that wrong?
It's not even 5 degrees.
How much?
295.
No, oh my God, no, that's way big.
Anyways.
Nobody?
I know why, I'm gonna get it right now.
Wait, I didn't take it to my.
I do. Ready?
I had it.
It's,
So, yeah, it's 6.
What is
Yeah, you
this?
should be getting right.
Oh, okay, wait, right,
Colin,
Oh, you didn't square.
right now, hold on.
Oh, it's each separate one is square.
you got what, who got? What Joe get?
3.574.
Okay, oh, shoot, I forgot right now, I thought it was 4 point something, but maybe it's 3 point something,
Is it really?
maybe.
I think it's 3.57.
If it's that,
I
I'm
forgot.
What did you use for your area formula?
1/2
base
base square.
squared.
Yes!
That's what I did.
I didn't get A and I got B. I don't know.
Look, what, okay, so, but here's the thing, right? To do the volume, you need, in here, you need an area, the area of your slice. Our slice is this, right? Our strip is this. What can I label this strip?
B.
B. What is this?
B.
Also B, because it's isosceles. They're the same.
Yes, I think.
So what's the area of this triangle? 1/2 base times height. It's 1/2 B squared. So it's just 1/2 the strip squared. It's just 1/2 the strip squared. And what's the strip? 4 minus.
That's it.
X to
That's
the fourth minus 2.3x to the third.
4 minus f of x.
Does the,
Yeah.
does the 1/2 of B square out that?
All of it.
That's part of the area.
No, because it's 1/2. It's 1/2 base.
Yeah, so the 1/2 is part of the area, so it should be squared.
No. The formula's not area squared. It's not area squared. It's the area of the triangle. The area of this triangle is 1/2 base times height. Right? So it's 1/2 B times B, so it's 1/2 B squared. Yeah. So the 1/2 does not have to be squared. It's the B that's squared. And the B is the strip. Okay, so Bo, do you see the part A? So the question was on part A. So this region's getting revolved around y equals -2. So we got empty space. All this empty space. So it's a washer. Big R, little r. Big R, little r.
That's what I always do, just.
Remember, revolving, anytime a problem is revolved or rotated, a region is revolved or rotated, it's going to be disc or washer, it's going to create circles, right? The revolving process creates circles, circle slices. So, and the center is, the radius is always from the center, which is where it's revolved around, right? So it's revolved around y equals -2. Both radii have to be on that. So the outer edge goes to the outside, inner edge goes there, but they both have to come from -2.
So what's the formula if the hypotenuse is?
So if it would have been the hypotenuse, okay. So now, again, how would you think through this? So on 49B, they said the slices are isosceles right triangles with the hypotenuse in the region. So the only thing that would change is you would have, here would be your strip, coming up off of here would be a right triangle. So now what you need is to know what that strip is. Well, that strip in this problem, this strip would be 4 minus f of x, right? That would be that strip. But now we'd have to think of a right triangle. We'd have to think of one of these, and we got to get our area in terms of this guy right here, right? We got to get our area in terms of that. So think back to trig. What do you know about the relationships between a 45-45 triangle? Okay, now if you go back to geometry, and I don't remember in trig if you did x, x, and x root 2 is the relationship. Or, a lot of you, I know, think of it more like this, right? This is root 2 over 2, root 2 over 2, and 1. And that actually works well, right? Because now we could call this our B if we want. I mean, since it's sitting there, you could call it your base, right, if you want to. But it's not really the base, right? It's hypotenuse, so maybe we should call it something else, whatever. It's called x. So we call that x, okay? And then I don't even like X. It's called H for hypotenuse. It's called H for hypotenuse.
Oh, that's height.
That's height. Jeez. Let's call it,
Okay.
Give up. German short.
okay, German short area. So what's this?
German short.
Root 2 over 2, German short area. Root 2 over 2, German short area. I don't care, call it whatever you want. But that's the relationship. So what is the area of a isosceles right triangle using these? What's the area of any triangle? 1/2 the base. Okay, I'm tired of calling German short area. I'm going to call it Z. And then height, root 2 over 2, right? In other words, you just have to label. I mean, we've been making up labels. We called S the strip because it was the side of a square. We called it D because it was the diameter of a semicircle, right? We just labeled it whatever. So here, let's label this something, and then we need to label the rest of it. It's the same thing we did for an equilateral. Remember we did an equilateral, we did this. We said this was 60, 60, 60. We said, okay, let's call this B. And then we did what we know about 60 and 30, right? We did that whole relationship, and we found out that this is root 3 over 2B. And then the area of this triangle is 1/2 times B times root 3 over 2B. So we just used stuff we should know to create it. So what is this? That ends up being 2 over 8, which would be 1/4 Z squared. So the area of the area of an isosceles right triangle is 1/2 a leg squared, or it's 1/4 the hypotenuse squared. Right? We just created that based on what we know about those things there. Okay? So you would have to come up with that. Now we could add that to our list, and we could have 7 things, right? We could have isosceles right triangle if the leg is in the region. We could have isosceles right triangle is this if the hypotenuse is what's in the region, right? And then so you got to draw the line somewhere on what you want to memorize and what you just want to be able to figure out on your own. So if you want to add this to your notes, memorize them, take an AP test, think it might be on there, go for it. Okay? So that would be how you would do 49D. As a matter of fact, I'm kind of curious if that's what they wrote on D.
3.574.
No, she's doing really
Sorry, Caleb, I forgot to ask you. Anything covered?
Oh. Well, wait a minute. That should work. Huh. Anyway, all right. Let's do. Okay, we got 10 minutes here, so you can have some work time. But let's go to this one. You don't have this.
No, if you don't want to sign homework, we don't have
That's not going to happen. All right. So, all right. Let's do.
I'll give you props.
Let's do B and C. But I am going to give you some work time because when you guys have idle time at the end of the period, you don't handle it that well. So, what are you talking about? Okay, so let's do B.
Are you throwing shots right now?
And I don't know what that means, but.
Are you throwing shots? I'm throwing this.
All right, B and C. B and C. Do C first. This is not one you have. You don't have this. Just do it in your notebook. This is from the 2009 exam. Okay, but you don't have this one, so just do it on your work. This one's a no calculator. Okay? Do C first. Do C first. Okay?
Other sides on the same page.
Do C first.
It's really easy. Is it supposed to be really easy?
Yep. Well, yeah, I think all these are easy. Whatever.
Oh, snap.
I'm telling you, you keep throwing shots at me.
Well, you guys do too.
Thanks, Derek.
Okay, then go on to B. If C's that easy, you gotta remember, you gotta work. It said don't do it, don't work it out. That's fine, you don't have to. But you do have to work out B. Okay, it's no calculator. So set up C and then now do B.
I don't understand. Region is base of this. Oh, okay. I think I got it. Are we supposed to evaluate or just
You have to evaluate B. You have to work out B.
with calculator or without?
Without.
I mean, that's stupid. When it goes from cosine to sine, the sine on the switches, right? The harder it makes.
Well, it depends. I mean, if you're doing derivative or
If you're going from cosine to sine derivative, if you're doing the derivative.
if you're doing derivative of cosine, it's negative sine.
So it would come out as a 2 or 3. Least now. Did you get 4? Is that right?
Anybody else get part B?
I'm about to get it this way.
Okay.
Anybody else? Who's the first person who got it?
Secret. Traded.
2 or 2.
So it must be easy.
Yeah.
Pretty good.
That's
good.
What's the cosine of 0 of 0?
What's
Alright.
the cosine of 0?
0.
That X value.
X value. Cosine is the X
I
value.
never thought of it like that until this.
Really?
Yeah. I remember how, I think I just memorized the triangle.
Kate talks about that. She
She
always
I
talks
think
about
she
X.
is. She said either memorize the unit circle
Right.
or memorize your triangles or something. Is all I really remember.
Well, I understand. Oh,
To be, I think it has to be a switch.
yeah,
Is that 2 pi?
No, it's 4 over pi. What'd you kick out when you did your antiderivative?
When I did my antiderivative.
You got to kick out something because of the pi halves in
Oh,
there.
I kicked out derivative, not anti.
You kicked out pi over 2. You got to kick out what? All right. Anybody else getting 4 over pi? Now, listen. Okay, so we'll go over part C first, but part B, the comment that somebody said right away in the other class when they read part B, because people were all kind of confused, and I saw some of those same looks. But then somebody in Part B they said, well, actually, isn't Part B just really easy to set up? And the answer is yeah. Why? Why is Part B really easy to set up? I heard the conversation, well, they don't tell you what the slices are, right? And that's the way we work it 99% of the time, right? These are the slices, and we spend most of our time trying to figure out what the area of the slice is, right? What they tell you. The area of the slice. They just gave you the area of the slice. They didn't tell you what they were, but it doesn't matter. It doesn't matter. All you need to put into your integral is a formula for the area of the slice. So when they give you the area of the slice, that's like, well, thank you very much, and then I'll just keep on going. Okay? And so so let's just talk about B. So that's all you need in there. Right? That's all you need is the integral of the area of the slice. So, and I remember when this question was on there was a lot of, teachers like, oh my God, or, that was so hard. Students thought it was so hard because they'd never done one like that because I don't know, as teachers maybe thought that's just too easy to just give it to them. But what they found out is a lot of students didn't understand the concept of what they were trying to do. Right? They'd memorize, oh, okay, if it's squares, I do this. And if they were memorizing strips and top minus bottom and all that stuff, but you're not thinking about the overall concept of what you're trying to accomplish. That you're trying to add up the areas, well, volumes, but that's the thickness. You're trying to add up the areas of the slices. So they just told you. Okay? There was one on last year's exam that was similar to that. We're gonna do another day. Anyway, back to C. The common mistake on C is you forget to go X equals. Because these are horizontal. You did it. Good, Spin. Because notice it says perpendicular to the y-axis, so they're horizontal. So it's this x minus this x. So it's the parabola minus the line. And then it's squared because they're squares, so it's just s squared, 0 to 4. And then you don't have to finish it. No calculator problem. And then don't forget here, we do this antiderivative, you got to kick out a 2 over pi. Okay? And then the antiderivative sign is negative cos, so you got negative there. And then when you plug those in, you get 2 over pi, because cosine of pi is negative 1. So that becomes positive, and that becomes positive, because you have minus and negative here. So it becomes plus, so it ends up being 4 over pi. Okay, so now I got the, and one of the things, and it actually didn't matter, look, a lot of you did pretty well, looks like, whoops. Okay, oh, I guess I erased it. All right, so in those same pages of the packet, let's work on this for a while. You've got your, the answer books right over there, so you double check your setups and everything. This is kind of some good practice on all the different types here, and then we'll move on.
This is 419.
This is, it's 419 to 421, I think, is kind of what pages those are on. Same as what we had before. And then, I think, if you're going to be gone tomorrow, I think the track, you're probably, wow, that was interesting.
Wow.
Trying to make that easier to read.
Sounds like ships.
There we go. All right. If you're going to be gone tomorrow, I'll have to give you something that we'll be working on tomorrow, but otherwise, that's your homework.
I did it yesterday.